This is going to be an overview lecture about color, including all the different types of primary colors for subtractive primary model, additive primary model, and um, also the regular sort of like paint primaries that you learned in kindergarten. So, but first let's talk about how we see, because that has everything to do with the way that we see color. So, first of all, we have this example here, the sun does its rays, it hits this apple, and then what we see is the color red. Okay, and what's happening is it's actually reflecting certain color. So the way that it works is that you've got this full spectrum light source, like for instance the sun, and it's going to emit full light, like a bright white light with all colors present at full strength. All right, and that produces a pure bright white light whenever you have all of the colors at full brightness. All right, and then that surface of the object will reflect and absorb spectrum rays differently. So in this case, the apple is reflecting red light and it absorbs the other light colors. And so what we see, what we perceive, is the color red, because the way that the reflected light enters our eyes, and our optical nerve translates that information and it goes to our brains, and we sort of see that as the color red. All right, so these are the spectral light primary colors. They're also referred to as additive light colors, or I should say additive light primaries. Red, green, and blue. These are going to be for like displays, like monitors, computers, phones, anything that passes light through it as its medium for color. All right. So, and as I explained a minute ago, in this example, red light is reflected while green and blue rays are absorbed. Okay, so that leads me back to the point that I already made, but I'll reiterate it. Whenever you have red, green, and blue all at 100% strength coming together, then you're going to have pure white light, and that's why it's referred to as additive primary color, is because all of those things added together give you pure white light. Okay, now the reverse of that then is whenever you get black in the additive primary color model, it's whenever you completely take away all light source, so 0% red, 0% green, 0% blue light rays, and you end up getting pure darkness or black, sort of like when you walk into a room and you flip off the switch so that all the light disappears and you see blackness. You turn the light on, you get all of the light rays coming in together, you get white light. Okay. So let's talk about the different primary color models. There are three different main models that we use, and those are going to be, the one at the top is what I mentioned. You see the little monitor off to the right, a little display next to it. That's the additive, and that gets you white when you add all of them together. And as I mentioned before, this is going to be in things like, anything that where the color of things is transmitted via light. So desktop displays, your phone, projectors, things like that. And the other thing that I like to also mention is, regardless of all these other primaries that we're going to discuss, I always like to think of light primaries or additive or spectral light primaries as being sort of the real primary colors, because if you think about it, it's light is the way that we see. If there's no light, then we don't see anything. You get blackness or you get dark, right? And so, or darkness. And so if you think about it, that's the original set of primaries. Everything is ultimately based on this red, green, and blue, spectral combination of light. So anyway, and then that also takes us then to print primaries, which you may have heard of, like CMY, and then a lot of times you'll hear K added at the end. K is the color black, so it's technically not a primary color. I'll describe why black is added later, but CMY, cyan, magenta, yellow, those are subtractive print primaries, and what happens is that because you don't have that pure whiteness that you would get, say, in the light primaries with red, green, and blue, where they all add together to create white, whenever you're dealing with CMY, you're actually dealing with ink, right? And so if you add those together, then you actually don't get white, you get sort of a muddy dark color, which is why the K is added at the end. It's a carbon-based black so that it makes blacks really richer. But if you've ever tried to, you know, print off your printer using just cyan, magenta, and yellow because maybe your black ink cartridge ran out, you'll notice that the blacks are not as rich. They're sort of like a sort of grayish or a muddy brown. And so that's why that K is added later to add the carbon-based black. Anyway, but and the way that CMY works is that it's ink that is printed on a white substrate, right? And so the presumption is that it's presented on a white substrate or a white ground or paper or whatever, because that brightness that reflects back through the ink color, it's sort of like if you go back to looking at light primaries, it's sort of like having the need for that reflectivity, that brightness, that whiteness, that pushes back through the color so that it gives you true color. So anyway, and you'll learn in a moment that the red, green, and blue and CMY primaries, they have a direct inverse relationship with each other. But anyway, so CMY is primarily for print. And then we have basic paint primaries, the red, yellow, blue that you learned about like in kindergarten, whenever you're mixing up compounded, you know, like pigments. And these are gonna be affected because of the natural kinds of compounds that you would find in Earth. You know, like for instance, there are different kinds of reds. There's like a cadmium red and excuse me, there's cadmium yellow, like blue, for instance, there's a cobalt blue versus an ultramarine blue. And so these different kinds of colors are affected by the kinds of physical compounds and mineral compounds that are put in the paints, and they have different reflective qualities in them. And so that's how you end up getting a slightly different kind of version of these primaries. And these are also, these basic paint primaries, these are also referred to as Newtonian primaries because Newton is the one who essentially sort of discovered and documented this first, and it was a very similar version to red, yellow, blue. It was slightly different. There was another one, but this is essentially what we use. Like if you're a fine artist and you're working with paint, you would base your primary colors off of red, yellow, blue, for instance, based on the way that paint pigments work. Okay. So let's look at this. Let's start with these primaries that you learned in kindergarten, right? Red, yellow, blue. And as I mentioned before, these are the Newton primaries, you know, used like organic compounds found in paint, like cobalt, cadmium, and so on. All right, this is a basic color wheel that's based off of the red, yellow, blue primaries, and all of these colors have relationship to each other. And you'll notice that the red, yellow, and blue, they're triangulated on the color wheel. And if you look at this color wheel, you can also, as you'll see later, as we go through this, you'll also start to see like how this mathematically makes sense in terms of the geometry of a circle and where color falls. And we'll get to that in a minute. Okay, but first of all, let's talk about secondary colors. So you've got primary, and in this diagram you see it sort of grayed out a little bit. The red, yellow, and blue, those are the primary colors. Well, if you mix them, you will get secondary colors. So red plus yellow, and this is something you probably learned in kindergarten or in first grade or whatever, but red plus yellow gives you orange, okay, as a secondary. Red and blue yields purple, and yellow and blue yields green. Let's talk about tertiary colors. So with tertiary colors, essentially all you're doing is you're adding a primary color with the secondary color that's next to it and creating something that's blended in between color. And for instance, red plus orange is going to yield red-orange. And it's important to recognize that the way that you always pronounce it is you always put the name of the primary first in the compound word. So it would always go red-orange. It would never, for instance, be called orange-red. So it's red-orange or blue-green, etc. Okay, and that's as far down as it goes. It goes primary, secondary, tertiary, and then any colors that are blended in between that, those are going to be intermediate colors, or just referred to simple intermediate colors. Okay, so color schemes, those are things that can help us as artists and designers devise limited palettes to use in creating harmonious color arrangements. So the first one we can talk about is monochromatic. So mono means one, chroma means color, so that means one color. The monochromatic color is essentially going to be one hue and the addition of white or black to create a range of tones within that single hue's range of values. And whenever we talk about white and black and the range of values, that means brightness and darkness. So value is going to always refer to brightness and darkness. Or another way that you can also refer to it is tints, tones, and shades. So tints and brightness are the same. Tones will have a little bit of white and black added to it. So it's not, essentially it's not the purest version of the hue or the color, all right? And shades are going to be when black is added. And so the way that you can kind of think about this, it's a little bit confusing at first, but whenever we're talking about paint primaries, right, we're talking about actual physical pigment, and that's what we're actually discussing at the moment. So the purest form of the color is referred to as a hue. So in this case, if you look at this screen and you see this yellow spot, that yellow spot would be the purest form of that particular hue. And then if you were to add white, that would be creating a tone. And if you were to add black, that would be creating a shade. If you were to add a little bit of white and black, then you're sort of desaturating it a little bit, and that would be some tone of the color. A lot of times if I'm referring to a continuous range of tones, it doesn't necessarily mean that I'm talking about something that has both black and white in it if I'm just sort of generically talking about tones. But technically speaking, whenever you talk about tints, tones, and shades, tones will have a little bit of black and white added. It's not the purest form of the color, which is referred to as the hue. Okay, so if you look at this, this is an example, for instance, of a picture, this picture of bananas. This is an example of something that is monochromatic, right? And you can see kind of how this particular image has a certain feeling as a monochromatic image. Okay, so another color scheme is complementary, and you may have heard the words complementary used before, and maybe you've heard it used correctly, maybe you haven't. Technically, there is an actual complement to a color, and it doesn't necessarily mean that it just sort of complements it because it looks nice. There is something that's called the complementary color that is directly across another color from it on the color wheel, right? And so, for instance, purple and yellow are complements, and red and green are complements, orange and blue are complements. These are really standard complements, and you'll notice in this case that these are primary colors that I'm using, and then the primary always will have a secondary complement, which is a little bit interesting. So, but you could have, you know, like a tertiary color that has a complement, and it's going to have some in between color too. But if you start off with a primary color, its complement is always going to be a secondary color that is directly across from it on the color wheel. And the point of complements is they vibrate a lot whenever you put them next to each other in some sort of adjacent arrangement. And so sometimes if you really want something to pop or have a lot of energy, complements are really good to use. And that's, you know, like in this particular comp, you see that this has got orange and blue, and you can see that it has a lot of energy in it, and it is sort of like a little bit sparkier, right, than maybe that monochromatic one that we looked at before. Okay, so another color scheme is a triad color scheme, and in which case you're going to have things that are triangulated on the color wheel. And it doesn't necessarily mean that they have to be an absolute perfect triangle on the color wheel. You can have a triad that's not, doesn't have this exact arrangement, but they are going to be essentially triangulated within a certain degree, so that you have, in this case, you've got a red, orange, and yellow, green, and a purple on this particular color scheme. And you can see how that looks. Again, if you go back and you look at this on the color wheel, you see that it's not a complement. It's basically splitting those complements, splitting where the complements would be. And so it's, maybe it doesn't pop quite as much as the straight complementary color scheme, but this one, it still has a lot of vibrance and a lot of contrast because of the arrangement on the color wheel. All right, and then there's another one called a tetrad, and what you'll notice here is a tetrad is going to have 4 colors, right? They are basically 2 sets of complements. And again, they don't have to be an exact arrangement of 4 colors across from each other, but it's usually somewhere in this range. But as I said before, you'll have 2 sets of complements. And in this case, you'll see that this sort of like a red-orange, the complement to that is like a blue-green, and a red purple is going to be, its complement is going to be a yellow green in this case. Okay, so, and then here is another example. Again, this pops a lot, but because now we've got more color, it's a little bit, I don't want to say muted because it's not really muted at all. It's very vibrant and everything, but it doesn't have the same edginess as potentially the other ones did. Okay, and then we also have analogous. Analogous is when you have colors that are adjacent to each other on the color wheel, and this is a 4-color analogous scheme. You could have like a 3-color analogous scheme, but this is a 4-color analogous scheme. And a lot of times these are often, this says these are offend, but it's supposed to say often. These are often used to create organic or kind of soft designs. Because the colors are so related, and you can see definitely how that differs from the other ones that I showed you before, right? Okay, so let's talk a little bit about the light primaries. All right, we have red. When we start with red, then if you add green, look what happens. You get a secondary color of yellow, right? And then if you add the blue color, look what you get as secondary colors for red, green, and blue, right? Remember, red, green, and blue are the light primaries. They're additive, and you'll notice this because if you add them at full strength together in this center of this sort of Venn diagram, you get pure white light, right? You add them together and you get white. But you'll notice that the secondaries happen to be cyan, magenta, and yellow. Those are actually print primaries, right? We talked about before, those are the kinds of inks that you would find as the primary colors in your printer. Well, let's find out more about how this all works. So let's start just by going over the primaries closely. So we've got red, green, and blue, and if you, as I mentioned before, and I'm going to kind of repeat myself a little bit because this is kind of confusing whenever you're learning it for the first time, and so I want to make sure that you really understand it, so I might reiterate things more than once. So red, green, and blue, additive light primaries, you add them all together and you add that to get white, pure white light, okay? And then the secondary colors, as I mentioned before in that last diagram, here's a different diagram so you can see if you add green and red together, that combination will yield yellow. If you add green and blue together, those primaries, then that combination yields cyan, and blue and red will yield magenta. If you look there, we have a red, green, and blue. Still, we're looking at a color wheel. It's a little bit different than the last color wheel that we looked at, which was based off of paint primaries. But this is what is going to be the standard for any kind of computer-based, artwork that's going to be displayed through an actual screen. So these are going to be the tertiary colors in between that. And then if you want to look at this, whenever you desaturate something, basically you're going from the purest hue, which if you look at this color wheel, the color that you see in these circles around the actual ring, those are going to be the hues within the color wheel. So the hue is at the color's fullest natural strength, and by adding them all together, you're going to reduce or weaken the strength of the other colors, okay? And so this is the way that you look at saturation. And then if you look at full saturation, the fullest saturation is going to be on that perimeter, exterior most perimeter of the color wheel ring. All right, and so the purest form of the color, as I mentioned before, is a fully saturated hue without any kind of white or black added. Okay. And so in this case, we're looking at yellow at its fullest saturation at 100%. Okay, and if you were to take that ring and sort of, let's make a little bit of a, like a 3D kind of diagram, then if you look at the ring at the top, right, and you see over here where I'm circling, that's the hue that's around the color ring I just described. And then if you look at saturation is going from the strongest representation of the hue all the way to sort of like this desaturated white color, or white, lack of color, I guess. Then if you were to drop it down to darkness, all right, it creates value. So from white up here to black down here, that's from full brightness to darkness, then that would be, for RGB, that would be the level of light that you're producing, right? And so remember, if you have full blackness, then that means that there's no light coming through at all in any of the light primaries. There's no brightness for red, there's no brightness for blue, there's no brightness for green if you have pure black. And so there's a range, if you want to look at this range kind of how you can get that color. So you can see here we have on the outermost part of the ring, we have, in this case, we're looking at red. So we've got fully saturated red, and then it's almost creates like this sort of cone shape. Or wedge shape, where if you desaturate at its fullest hue strength, right, fullest brightness, and you desaturate, then you're going to get white light, or you're going to go towards the white light. That would also mean that the other colors would have to be in some way working with you, right? But you've got this full saturation, and then if you reduce the value, it's going to go down towards blackness. And you'll see along this left edge of this cone or wedge shape, we basically have pure grayscale, where it goes from essentially pure white to the blackest of blacks, right? And then as you move inwards, like you start to get some tones where you've got a little bit of black, a little bit of white, right? So that's kind of the way that that works. And then if you look at these side by side with a sort of swatch value, you can start to see how we get like swatch colors, right? And then you see here this value, pure white down to pure black, right? And that's, this leftmost edge is a full pure grayscale, all right? And then at the top level up here, we have on the far right, on the top, we've got the pure red hue all the way to the bright white color, and then you've got, these are going to be referred to as tints. So any kind of tint would be essentially the hue plus white, all right? And then if you were to go down in here, then what you end up having is shades, right? So if you were to take this and you drop it down, these are going to be shades, for instance, of that red, and so on, okay? And then if you look at that same swatch panel, that cone shape, and then you look at a modern color picker, say like in Photoshop, for instance, or in Illustrator, you end up looking at a very, very similar kind of thing. And now the color picker should start to make a little bit more sense. And you'll notice that up in the top right corner, that is going to be, in a color picker, the purest hue. And you'll see here where it says H over in this diagram, it says H is 0 degrees. That means that it's at the 0 degree place on the color wheel. And you'll also notice where the slider is. The slider indicator is down here. And the way that I like to look at this color strip right here that I'm moving my mouse over, that color strip is going to be like, if you were to take that as a, let's say like a piece of paper, almost like a litmus piece of paper, and then you lifted it off and then you sort of wrapped it around and made the ends meet, you'll see that down here is a purest color of red, and then up here is a purest color of red. And so you can start to see how that completes the color wheel circle, okay? And that these are purest forms of the hue, okay? And so if you were to pick from the slider, if you made the slider move, that means that the hue is changing. Okay, if you want to stay within a hue's individual range, then you would never move this slider. If you only wanted to get certain sample colors within the lightness and darkness range of a single hue, you would move the slider. You would just move where you're picking from this area in here. And so you see here the hue is 0. And if we take a look at this color picker, like I said before, you've got red at its maximum level. So red here for the RGB scheme, right? So red is 255. Whenever we're talking about digital color, color channels will have up to 256 possible tones or possible colors, levels of light, I should say. All right, so you have anywhere from 0 to 255. 0 actually counts as something. So 0 to 255 means that that's a full 256 possible colors, so or possible versions of red. And so if you have it at its fullest strength of 255, that means that it's its fullest cleanest version of the hue, and you'll notice that there's no green present, there's no blue present down here. You see that those are completely at 0. That means that we have the pure hue, and you'll notice the slider is located down here. The color picker has its chosen selection up here. And then you'll also notice that magenta and yellow are essentially at their fullest levels. And remember, I told you that RGB has an inverse relationship to CMY, right? As different color models. Well, if you remember from looking at, the magenta and yellow, it would yield red if you were to go to that color primary and color model and you were to add magenta and yellow together, that would produce red. Okay, and so you can look at this inverse relationship, and it's really handy. And by the way, this right here where it says FF0000, that is a hexadecimal number, and that's used for web stuff primarily, and any other kind of digital RGB types of files. All right, and so if we look again, this just reiterates what I was already saying, but it's now we're talking about saturation and brightness. So it means that it's 100% brightness and 100% saturated. So this is how you can start to look at some of these values and understand how they're contributing to the color that you're actually getting. Okay. All right, so now if you look at yellow, okay, you see that its value is at 60 degrees. So that means that on the color wheel, if this strip right here were created as a single band, that was connected in a wheel shape, then that means that it would be at the 60-degree mark geometrically on the color wheel. And you'll notice that it's, again, fullest saturation, fullest brightness, that it is now red and green combine, because red and green combine, the secondary color is going to actually be yellow. Right? So because remember, we're talking about red, green, and blue. Some people might go, wait a second, yellow is a primary. No, yellow is only a primary in the paint pigment primaries, like that we talked about earlier, like the stuff that we learned when we were really little kids, using finger paints and stuff like that together, right? But if you look at this, red and green added together as primaries and light primaries will produce yellow. Okay, and then we can look at green. Again, green, it's at 120 degrees on the color wheel, and you see here its green is at its highest strength, 255, and there's 0 red present and 0 blue present. Okay, remember green is a primary for additive light. And then 180 degrees, right, we end up with this cyan color, roughly, right? And so what we have is green and blue added together at their fullest strength, and it's at 180 degrees on the color wheel. All right, and you'll notice in this case, this cyan color is the complement to red, because if red is at 0, right, 0 degrees, directly across from it would be 180 degrees, right? So that's another way of mathematically knowing what the complement of something is where it's located in its hue degree arrangement. Okay, and then 240 is blue, 300 is magenta, and back to 0, ultimately it's 0 to 360, right? That's going to be red again. Okay, so we're back to red, and you'll notice that the slider up here is all the way at the top, and when we started it was all the way at the bottom. So like I said, it would be like taking this strip and curling it around on itself and making it meet and putting a little piece of tape on it, and you've got red and red, okay? And then this is another way you can look at it, all right? Okay, and then another way you can look at it. And then you can think of 0/360, okay, where these two things meet. All right, and that kind of explains a little bit more like what I was talking about before. So hopefully that'll really help you understand when you're looking at modern color pickers, like how color works, and even if this is confusing stuff, and so it takes a little while for you to fully understand this kind of stuff, but this way you can actually look at color pickers and you can start to understand saturation, brightness, hue, and you can understand the levels of color in terms of RGB with like 0 to 255 and so on. Okay, and then let's take another quick reminder look at this. So on the left is an additive light primary color model, which is red, green, and blue. And then on the right, you'll see it's the subtractive color model, which is CMY, and then K is the black color that's added. And let me sort of go back over, how this works. So whenever you have light that comes into your eyes, and this is the way that we see things, those primary colors are going to be red, green, and blue. So I think of that as the foundation of all other primary colors, all other primary color models, right? This is the sort of the granddaddy of them all, right? It's the original one, because without our eyes, none of this color stuff would even really matter. It wouldn't be color. It wouldn't matter to us. Okay, so excuse me, where we have red, green, and blue added together, you see in the very center over here, you get pure white light. Now, as a reminder, the way that this works as subtractive primaries is that whenever you are printing something, oops, I misspelled subtractive. This is supposed to be SUBTR. Okay. Anyway, whenever you have these colors together, yellow, magenta, and cyan as inks, you're going to lay that ink down on something, right? Whether it's going to be a white piece of paper or a red piece of paper or a green piece of paper or whatever. And because ink has some translucency, right? You can kind of see through it a little bit, right? It depends on the brightness of whatever the substrate is, and or the color of whatever that substrate is to produce its ultimate final color. And so yellow, magenta, and cyan have a presumption that it will be printed on something white. So if you have something that you've got in CMYK on your computer and you're working on a file that's going to go to print, then the thing that's important for you to understand is that the assumption that what it's going to be printing on is white. Otherwise, you cannot count on the color looking the same. And that's also why sometimes when you print stuff, it will look different than it did in your computer screen. Typically, whenever you print stuff, it looks darker than you maybe saw it on your computer screen, unless you've got everything calibrated, which is actually quite complicated. But if you look at something on your computer screen in CMYK, it is going to look a little bit brighter probably than it actually will print. And that's just sort of a general rule of thumb that you should consider moving forward. And part of that is because anything that is pushing light through, like a display on your computer, to produce color is inherently going to be bright looking, right? And so you don't know necessarily, unless you have calibrated or you've like really selected it for a very specific reason, purpose, you don't know exactly how bright your paper is going to be, and you don't necessarily know what variances might be in the cyan, yellow, and magenta, and how that particular ink is going to get laid down by that particular printer. And so sometimes you have to do a little bit of testing if it's something that's really, really important. And that's why if you send something to like a printer, you would always want to get that particular printer's proofs so that you can see how it's going to look before you go to press on something and spend a bunch of money and do a big run. And if the color's wrong, then you don't want to find out after you've printed the entire run. Okay, so that brings us back here, and this is where we get to CMYK. All right, and so this is that same picture with CMY added. Okay, this doesn't actually have K. All right, this is without the black, and you can kind of see how some of the darks are a little muddy, right? Because we're using all the other colors to create black. And so if I look at this next one, you can see what the color separations are. You can see where the cyan color is laid down. You can see where the magenta color is laid down. You can see where the yellow color is laid down. And all three of these would be separations that a printer would run through on their printing press with these individual colors so that the final press, whenever it gets laid down all together, it produces something that actually looks like the thing at the top. Now, if you wanted really rich black, you need to add that black layer with the K, right? And that's a carbon-based ink, and that's going to give your blacks a much richer looking feel, as you can see here. Okay, and this is referred to as process color, where you've got separations and you're combining colors to create other colors, right? So this is the way that that would look on like a press that's going to do halftone printing. And this is just sort of like a detail up here where it's circled. On the left, you can see like right here, you can see that this is what that detail might look like as a halftone print, where you've got different versions of the original colors laid down so that it produces something that from a distance visually appears like it does over here in the zoomed out version. Okay, and that's, again, I said, referred to as process color, where you're processing multiple different levels of color, adding them together to create the ultimate final effect. Okay, and it's also referred to as a 4-color printing process. So if you hear process and you hear 4-color printing, CMYK printing, all of those things are the same. So 4-color process, basically it takes percentages of cyan, magenta, yellow, and black, and it puts those in halftone patterns so that it creates this blend, this visual blending method, so that whenever we look at it from a distance, you can see it as a single color, as these different sections as single colors. And that's also why if you ever hear someone talking about, you know, what size the halftones are, or the screens are supposed to be, then the larger, as you can imagine, the larger the dots are, the larger the halftones are, and the more they're separated from each other, sort of the less visual detail you're going to have, and you know, the color's not going to look as good. A lot of newspapers, for instance, will use you know, and inexpensive prints are going to use larger halftone patterns, and really, really high quality, let's say art books, for instance, that have, you know, artist plates inside of it. Those are going to have a really, really small and fine halftone pattern, so that the color is very dense and that you can't see any of the printing pattern at all. Okay, now there's another thing that we're not going to get into immediately, but we will talk about this later in the semester, but I just want to introduce the concept to you right now, and that's a thing called spot color. Spot color is also referred to a lot of times as like the PMS system or the Pantone matching system. There are other kinds of spot color systems that are not Pantone specific. Pantone is a company. There are other companies that make spot color inks, but basically the way a spot color works is it's special because it's an individually formulated ink color that printers can use to achieve the exact same color in graphic and line art, no matter what printer they're printing on, right? It's primarily used like in logos and design with a very limited color palette. And the reason you might want to do this is, for instance, like if you're McDonald's, then you have the budget to probably have a special color made up just for your brand that nobody else can use, for instance. And that's going to be, you know, the color of the arches, like the red and the yellow. Those are very specific Pantones whenever they have print materials done. And same is true like for UPS. They have their own specific colors that are made up, and the way it works is that there's a place that formulates the ink and makes a lot of that ink, and then the printer, any printer anywhere in the world, can order the ink with that specific ink formulation, and you know that that ink is always going to produce the exact right color, no matter what you're printing, where you're printing, who's pressure printing on, and so on, right? Whereas process color or 4-color CMYK stuff is, you know, you don't like, you're using whatever the ink is that came from that printer, and it might have a slight variance in color than the ink that's at a different printer, or it might even have a slight variance in the ink that they get, you know, 2 years from now, right? It might, the new inks that they get might be slightly different. And when it matters a lot to you that the color is spot on perfect, then that's whenever you use spot color. All right, for something like a logo or something like that. Okay, anyway, that is the end of the color lecture. If you have any questions, please feel free to ask. Color is actually quite complicated. There's a reason that everything prior to this has been in black and white. Just let me know. Happy to help.